Hello and welcome to this video. In this video, I want to solve this question with you so that you can be able to see how we use the concepts that we have learned in a previous video. But I'd like you to just pause the video, attempt the question because I know you've got some ideas on how this question is supposed to be solved, and then come back and play the video. If you've not watched the video, please ensure that you do that so that you can be able to understand the concepts that we are going to use in this question. So go right ahead, pause the video, and then come back. Okay, welcome back. Let's read the question together. In this question, you are told that the figure shows an arrangement of 6 springs of the same length and a spring constant of 300 Newton per meter. And we know what this means. It means that a force of 300 Newtons is required to produce an extension of 1 meter in a single spring. Assume both the springs and the connecting rods, they are light. In other words, their weights do not count in this question. A mass of 300 grams is suspended on the system. And at this point, I want you to know that 300 grams is the same as 3 newtons. Let me change the color to blue. Yes. So the force acting is 3 newton. I'm using a very simple conversion unit. 100 grams is equivalent to 1 newton. Determine the tension in each spring. Now, over here, the force that I exert on the system is a force of 3 newtons. I can start by the spring which is immediately after the 3 newtons. You can see that this spring supports all this force by itself. So when I use the equation spring constant K is equals to F over X, and I want to get the value of X, I just need to divide the F by the value of K. So for this spring, the force is 3 newtons and the value of K is 300 Newton per meter. And you'll be able to see that this one will give me 0.01 meters, which is actually equal to 1 centimeter. So the extension produced here is 1 centimeter. How about the extension produced in either D and E? By the way, the extension in D is equal to the extension in E. So we are just going to calculate one of them. Again, I use the same equation, which is X. I can call this one X produced in spring F. This is X produced in spring D. Again, I need to divide the force by the value of K. How much force? Remember, if springs are arranged in parallel, they will share this force. So each one of them will take 1.5 newtons. So 1.5 newtons, again divide by 300 Newton per meter. If I manipulate that, I'm going to get an extension of 0.005 meters, and this one is the same as 0.5 centimeters. Another way of quickly knowing the extension here after calculating the extension there is to argue out like this. If a force of 3 newtons produces an extension of 1 centimeter in a spring, how much extension will be produced by a force of 1.5? And you'll see that it will be half of that one. But we have proved the extension anyway using this calculation. We can also use that concept over here where we want to know the extension in one of the springs here. The extension in A is equals to the extension in B is equals to extension in C because they are parallel. Again, let me say extension in spring A, the force acting on that spring will be 1 newton. 1 newton. divided by the value of the spring constant, which is 300 Newton per meter. And this one will be like 1 over 300 meters. I think this one is supposed to give me 1/3 of a centimeter. 1/3 of a centimeter. And I can leave it at that, or even go right ahead and simplify it into 0.333 recurring centimeters. You can see that the least extension will be produced in the springs A, B, and C, followed by D and E, and finally the one with most extension is F, and we know the reason why. It is supporting the largest force, while this one is supporting, each one of them is supporting 1.5. Over here, each one of them is supporting 1 Newton, 1 Newton, 1 Newton. So the extension in each spring is known. Over here, it's 1/3 of a centimeter, or 0.333. Over here, it is 0.5, and over here, it's 1 centimeter. The next part is to, and by the way, we already have the tension in each spring. I forgot about this part. The tension here is 3 newtons. The tension here is 1.5 newtons. And the tension here is 1 newton. So 1 newton, 1 newton, 1 newton, 1.5, 1.5, 3 newtons. So that one is done. So the tension in each is done. The extension in each spring, I've just shown you how it's worked out. And then the total extension of the system. The total extension, X total, is equal to this extension here, which is 1 centimeter. This extension here, which is 0.5 centimeter. And the extension there, 0.33. Recurring. And here we are going to get 1.833 centimeters. That will be the total extension of the system. Of course, I can get this one in meters. It will be 0.01833 meters. Because in part D, I want to get the spring constant of the spring system. So K of the spring system is going to be equal to the force that the spring supports, the spring system supports. It supports a force of 3 newtons divided by the total extension. So over here, I've got 3 newtons divided by 0.01833 meters. And this one will give us, so I'm going to divide 3 by 0.01833, and I get a value of 163.7. The value of the spring constant is 163.7 Newton per meter. And that is the value of the spring constant of the spring system. Now, can we be able to get the value of the spring constant in terms of K, where K is a spring constant of one of the springs? Is that possible? So this is what I'd like you to do. I've gotten rid of all the inking on this slide. The spring constant for one of the springs is K. Now I want to get the spring constant of the spring system in terms of K. Is that possible? Let's find out. The force we suspend over here will just be F. So the extension I get at this point, X in spring F, is going to be equal to the force divided by K. How about the extension I get in D? It's going to be equal to F divided by 2 over K. This one will be F divided by 2K. How about in A? Remember, the extension in D is equals to the extension in E. That is why I'm just calculating just one of them. How about the extension in A? Again, it's going to be equal to the F, which is F over 3. I hope you understand why here I've divided by 2. Here I'm dividing by 3. And here it is just F. Divide by K. Again, this one is going to be equal to F over 3K. So let me get the total extension, XT. It's going to be equal to F over K plus F over 2K plus F over 3K. At this point, we are adding fractions, and when we add fractions, we want to use the LCM. So the LCM is definitely 3K. K goes into 3K 3 times. 3 times F, I get 3F. 2K goes into 3K 1.5 times. In other words, if I divide 3K by 2K, I get 1.5. So 1.5 times F gives me 1.5 F. And of course, this one goes here once. 1 times F is just F. This is a 5.5. 5.5 F. You know, 3F. Let me just complete this just to verify that this is 5.5. 3F plus 1.5 will be 4.5 F. 4.5 plus 1F will be 5.5 F. Oh, this one is 3K. Sorry. This is 3K. That is the total extension. So let me get the value of K now. KT is going to be equal to the total force divided by the total extension, XT. Here, the F is this much, divided by 5.5 F over 3K. This one is going to be equal to F times 3K, because we are dividing by a fraction, is like multiplying by the inverse of that fraction. And of course, here I've got 5.5 F. At this point, we'll just be able to see that the F's will cancel out, and I'm remaining with 3 over 5.5 K. And what does that give me? Let me change the color. 3 over 5.5 3 divided by 5.5 gives me 0.45545454 repeating. So I can say it is 0.54 K. And what was the value of K, by the way? The value of K is 300 Newton per meter. Let's see whether KT will give us the same value that we got previously. So we are going to say this one will be 0.54 times 300. Let's see what we are going to get. So times 300, and I'm going to get 163.63 recurring. 163.6 Newton per meter. And you can see we get the same answer. And this is how we would work out a question like that. Now, there is, of course, another quicker way of getting the extension in a spring system like this. For instance, if the extension produced here is x, that produced here will be a half of x, because the force in each one of them has been reduced to half its previous value. Remember, here it was 3 newtons, here it is 1.5 each. And the extension is directly proportional to the force. So if the force is halved, the extension is going to be halved. If the force becomes a third, the extension will also be a third. So here, I'm going to get a third of x. Remember, I'm basing it on the fact that the extension here is x. When we add all these extensions in order to get the total extension, we are going to get 1x plus a half x plus a third x. This what gives us the LCM of 3. And over here, I will have 3x. Over here, I'm going to have 1.5x. And here, I just have x. And that is what is going to give me this 4.5. I'm going to get 5.5x over 3. That will be the total extension. And then now from there now, I can go over and now calculate the value of kt, which will be given by the total force acting on the system divided by xt. How much is the total force? It is this F that we have around here. That F that we have there. And remember that X over here was equal to F over K. So at this point where we say that xt is going to be equal to 5.5 divided by 3x, it can be written as 5.5 divided by 3. The value of x is actually F over K. F over K. And this is what gives us 5.5F over 3K. And if you trace back our solutions or our problems, you'll find that there is a point where you got a value like this one here. So all I need to do is come and put the value of F here. This F, this xt is this one here. 5.5F divided by 3K. And just like before, when we divide by a fraction, we have to multiply by its inverse. So we multiply by 3K over 5.5F. And once the F's cancel out, I have my value of 3 over 5.5K. And I've been able to express the spring constant of the system in terms of the spring constant of one of the springs, because K is a spring constant of one of the springs. That is how I would do it. You know, we are trying to understand this question from all angles. And since we gotten this point, in order to prove that the spring constant is 163.7, we're just going to introduce the value of K, which is 300 Newton per meter, and we're going to get the same value. So the point I want to make here is this. If you know the extension here, just divide that extension by 2, because that is what you're going to get there. And just divide that extension by 3 to get what you have there. And I hope from this angle, you're trying to see the question from a different perspective altogether. That's why I'm using as many methods as possible, so that the one which appeals to you, you can quickly pick that one out and leave the rest. And that is how you would look at the same question from a different perspective.